So, welcome everybody to the sixth lecture of wireless communication systems. In today's lecture, we will continue talking about wireless propagation characteristics, and specifically we will talk in depth about power delay profile and Doppler power spectrum. So let us review very quickly what we have taken in the previous lecture. So basically, we discussed the autocorrelation function related to the time-varying impulse response, how to find it, and for the case when you have the angle of arrival, your paths are coming from all the direction and the distribution of the angle of arrival is covering the angles from 0 to 2 pi, and you have the in-phase component of your received signal and the quadrature component of your received signal. Then in this case, we assume that we have wide sense stationary process, and we said wide sense stationary means that the mean of your random signal is 0 and the autocorrelation is independent of the instantaneous time, but rather depends on the time difference, tau or delta t. And accordingly, you have your autocorrelation function with respect to the in-phase component, which can be given as follows, and which is exactly equal also to the autocorrelation related to the quadrature component, because your received signal is complex, as we explained in the previous lecture, have in-phase component and quadrature component. We found the autocorrelation related to the in-phase, and we found out that it's exactly equal to the quadrature component, and then we also showed how the Doppler frequency is equal to the velocity over lambda, and for any theta you put cosine theta in. So now this is the autocorrelation with respect to the in-phase and quadrature component. You have also cross-correlation between the in-phase and the quadrature component, which can be given as follows, and this is exactly equal to the negative value of the cross-correlation between in-phase component and the quadrature component. So you have uniform angle of arrival in narrowband model. In-phase quadrature component have 0 cross-correlation at lambda at distance equal half lambda, or exactly 0.4 lambda, this shows actually the autocorrelation function of the in-phase and the quadrature component of your received signal, which is random, and we characterize it by its autocorrelation to know at which distance far from my position the signal will change dramatically or will have independent value. So we have seen that the autocorrelation function can be written in terms of Bessel function J 0 2 pi fd tau, where tau is the delay spread and fd is the Doppler spread. And since the cross correlation value becomes 0 at 0.4 lambda, then we say that the signal decorrelates over roughly half a wavelength. And we also discussed the relationship between decorrelation, independence, and orthogonality as well. So the power spectral density, if you were to find the power spectral density, then you would need to take the Fourier transform of the autocorrelation function, and the Fourier transform of this figure gives you this power spectral density at the maximum Doppler frequency. So the Doppler frequency maximum spreading, it has at maximum value happens at fd, which is the maximum Doppler spread. And we usually use this in our system simulations to get values and to use them in our simulator so that we can find the performance of our system in terms of bit error rate and throughput. After that, we talked about signal envelope distribution, and basically this envelope, you can understand it as the amplitude of your signal. We said since the signal R has Ri in phase and the quadrature component JRQ. What's the amplitude of this? We said the amplitude is square root of Ri square plus Rq square. So this amplitude of R, we studied its distribution, the probability distribution function. Ri, by assumption, by nature, has normal Gaussian distribution. Why is that? Because we have large number of random signal reaching the receiver at the same time. This nature of large random number of received signal causes, based on central limit theorem, produces Gaussian distribution. So this is Gaussian and Q also Gaussian. Now the amplitude of R, which is equal to the square root of the in phase plus the quadrature square, we found out that it has a different distribution, which is, we call it Rayleigh. And Rayleigh can also be generalized to the cases where you have line of sight between the transmitter and receiver. In Rayleigh distribution, there is no line of sight. Now, there are cases where you have line of sight and fading. When line of sight component is present, you have Rayleigh distribution. Rayleigh distribution, we have a new parameter in the system model, we call it K, and K changes according to the environment characteristics and geometry you have. For example, when K is large, then there is large probability that you have line of sight link between the transmitter and receiver. This is Rayleigh. Also, we have Nakagami. Nakagami distribution also similar to Rayleigh, but it gives you the distribution in a more general form where you basically have a new variable called M, and this corresponds to the amount of fading you have in your system. And when M is equal to 1, I will have exactly Rayleigh. When M is equal to 2 or 3 or 4, any other values, you will have fading with different intensity. And we need these models in order to analyze and characterize our system and be able to derive the probability error performance and other performance metrics as well. So this is what we talked about. Then we moved to wideband channel, and we said the individual multipath components are resolvable in this case. See the previous case when I was talking about the distribution, all the multipath components were reaching the receiver simultaneously at the same time. However, if these multipath components are reaching at resolvable times with delay, too much delay that the receiver can distinguish, then we will have something we call it spreading, delay spread. Yes, you have bunch of rays reaching at this tab at this time, multiple waves reaching at this time, and this is the shortest window the receiver can see. And another bunch of tabs which get reflected off another building, you receive them after delta T1. So at each tab here, you have the previous distribution, which is Rayleigh, Rayleigh, Nakagami, whatever. Because you have multipath components, large number of random received signal that are added to each other constructively or destructively. This nature of addition of large number of random variables which are assumed to be Gaussian gives Rayleigh envelope distribution or Rayleigh or Nakagami, whatever, based on the environment. Now, when you have resolvable multiple tabs, not only 2 tabs, you might get 10, 20, 60 tabs based on your environment and your resolvability at the receiver. The larger the bandwidth of your signal, the more you will be able to resolve multiple paths. So in this case, a new impairments, a new feature of the wireless signal appears, which we call it delay spread. And this delay spread is very critical phenomenon, happens in the wireless environment, the wireless medium, that we need to tackle it and handle it in an efficient manner so that we don't let it disturb our communication system. So what's the condition for this to happen? We said that the delay spread, the difference between delta tau, the difference between the last received resolvable path and the first received resolvable path should be greater than the time duration of your transmitted symbol. You have transmitted a symbol like this. This is pulse. Yes, this is pulse. This is the duration. If the spreading in your channel like this is the duration of symbol. If the spreading is larger than this, the duration of your channel spreading larger than the duration of the symbol you are transmitting, you will have delay spread, multi-path delay spread. And this causes inter-symbol interference. Why? Because you have your symbols here back to back. And as you know from signal and systems, when you send your signal over a channel that has this delay spread, your signal gets convolved with the channel. When you have a signal of this duration, yes, everybody remembers with me signal and system because it's very important for you to understand the effect of delay spread. When you have a signal of this duration and a channel of this duration, what would be the result? What's the duration of the result? You will get another signal that looks like this, that has a duration equal to the duration of this T1 plus T2. So if you are sending your signals back to back, what will happen to the signals? They will interfere with each other. And this interference prevents you from being able to recover your data successfully. We need to avoid that. We need to bring new mechanisms, new techniques. And the inter-symbol interference happens not only because of the channel, but also because you want to transmit your data with high speed. You want high-speed internet. High-speed internet requires you to send symbols back to back very quickly. If you are sending your symbol back to back very quickly, what happens to the duration of the symbol? Shrinks. And it shrinks to a level where its duration becomes less than the spread in your medium, whether optics or copper or wireless or transmission lines or whatever. In this case, definitely you are going to face inter-symbol interference and delay spread in your channel. Two reasons: the channel, the filter you use at the transmitter, and the speed of data rate. All of these, as a wireless engineer, you need to know your application and your situation and adjust your design accordingly. So this duration is basically the duration of your signal is also 1 over its bandwidth. That's why here I put that when the time difference between components in the channel exceed 1 over signal bandwidth, this phenomenon of delay spread happens. You cannot escape it. This is what are you going to get. Yes? High-speed wireless systems are wideband for most environments. See? High-speed wireless system. High-speed wireless system. Not speed by movement, speed by transmission. Now, we need to understand and look at scattering function. What's a scattering function? You remember when we talked about the time varying impulse response, and we said the time varying impulse response can be written in terms of C, tau, T. If you assume that this is deterministic somehow, and you take the Fourier transform of it, you get a deterministic scattering function. So scattering function is something that's in the other domain, in the frequency domain somehow. So for example, when you have your channel C tau of t and you take the Fourier transform, then you integrate and multiply by exponential to minus j2 pi bt, and whether you integrate with respect to time, then you have this scattering function. So scattering function is nothing new, but different way of looking at your signal to get more insights, more information that can be helpful later on for you in your design. Yes? And this is how we characterize it actually. And the underlying process, as usual, wide sense stationary, wide sense zero mean, autocorrelation independent of the instantaneous time but dependent on the delta t, the difference in time, and we have Gaussian distribution. The received signal, they are large, and that's why they form Gaussian by central limit theorem. So only characterize mean zero and correlation. Autocorrelation can be written as the autocorrelation function, A for autocorrelation and C for the channel, and these are the delays, tau 1, tau 2, delta t. So this can be reduced to this form. Correlation for single multipath delay time difference. This is actually for single multipath delay time difference because you are taking two tabs successive to each other and you try to find the correlation between them. And you can generalize it as well. Now what we are interested in, since the channel is random, yes, we will get random scattering function. And this random scattering function becomes function of tau and rho, where tau represents the delay spread and rho represents the Doppler spread. And you can get this by taking the Fourier transform of the autocorrelation function of your channel with respect to delta t. And this is the mathematical equation you use to get that. For example, I gave you the channel, see this one. From this you can get the autocorrelation function, and when you take the Fourier transform of the autocorrelation function, you get the scattering function of your random signal. And when you plot it, you get a curve like this, where this is the x-axis tau, and the axis inside the wall is rho, which represents the Doppler spread. Multipath intensity profile. In multipath intensity profile, instead of taking this autocorrelation in general, you are keen to know only the effect of the delta tau delay, as the name implies. Here you have power delay profile, multipath intensity profile. For this case, yes. No, it's not negative. It's not negative. So in this case, the autocorrelation function, if you are interested in just finding in terms of tau, you put delta t equal to 0. You assume, if you want to get just the delay spread, you assume that you don't have variation in times. If you don't have variation in times, you don't have Doppler spread, then you are focusing only on the delay spread. Autocorrelation of tau when delta t is equal to 0 reduces to this form, autocorrelation of tau, and this determines the average and RMS delay spread. This is the RMS delay spread. It's a quantity that shows you the spread in your channel. And this is the function when you draw it for a certain channel. Approximates maximum delay of significant multipath. Now, what's the important thing about this? What do you need to know about that? Once you know the RMS value of your delay spread, you can guess what's the coherence bandwidth of your channel. What's the coherence bandwidth? The coherence bandwidth is the range of frequencies over which your channel response looks similar or correlated, not independent. For example, if I tell you this is your channel, so these values are highly correlated to each other. Once you have value like this becomes independent of this. This is not random, exactly random. The value here very close to the value next to it, very close to the value. So these values adjacent to each other are correlated with high percentage. Now this, for example, suppose this is the channel until you define the coherence bandwidth, the range of this, the x-axis is frequency, let's say. The range of frequency over which the channel seems correlated. So you will say this is the coherence bandwidth of the channel. The channel seems to be similar within this region. After this, behaves differently. So if you transmit a signal whose bandwidth is larger than the coherence bandwidth of your channel, you get Doppler spread. You get delay spread, sorry. You get delay spread. If it's below, you don't get any spread and you get just multipath, the construction of the...
This also gives you the highest power, the channel.
True, yes. So this is the concept of coherence bandwidth. Maximum frequency over which the Fourier transform of your autocorrelation function, this is what I was talking about in math. This is in graphics, in visualization, this is in math. You take this is in time domain, let's say, autocorrelation function in tau. You take its Fourier transform, becomes function of frequency. And the Fourier, if it is greater than 0, this means that they are correlated. Once it becomes 0 or less, uncorrelated. This is how you calculate it mathematically. So when this value holds, this implies that signals separated in frequency, they are independent, uncorrelated, and you say they are separated by delta F, and they will be uncorrelated, and it looks like this. This with this, they have zero correlation. We know this. The delay spread is greater than your simple duration. You get delay spread when the spreading of your signal, when the duration greater than the bandwidth, the 1 over the bandwidth. And here you have ACF. This is the coherence bandwidth of your channel, and the black one is the bandwidth of your transmit symbol or signal. Once the bandwidth of your transmit signal is larger than the coherence bandwidth of your channel, you will end up having delay spread, and consequently you will get intersymbol interference that you need to handle it at the receiver. Now, this was multipath intensity profile, or we call it power delay profile. We have also Doppler power spectrum profile. In this case, let's start from the general formula where the scattering function of tau and rho is equal to the Fourier transform of the autocorrelation function. The Doppler, if you were to find power spectrum profile, then you need to eliminate tau, and just you are interested to have it in terms of rho only. You take the Fourier transform with respect to delta t, but instead of putting delta t equal to 0 as in the previous case, you put delta f equal to 0, because in this case you have no frequency variation. Delta f equal to 0. With respect to variation in time, variation in times produces Doppler spread, because it's the Fourier transform, Doppler in frequency domain. When you take the variation, you get the spread. So, and this becomes the autocorrelation function of the channel with respect to the difference in time, and you get something like this if you have Doppler spread. This is the amount of Doppler spread you have, and this is the scattering function related to Doppler, and that's why we call it Doppler power spectrum. And gives you power of multipath at given Doppler. Doppler spread is equal to BD. We call it the maximum Doppler for which the scattering function is greater than 0. And you have, in this case, what can you determine? The coherence time. The coherence time is equal to 1 over Doppler spread. Now you have two critical information. Coherence time and coherence bandwidth. Coherence bandwidth in the previous slide related to Doppler spread. Coherence time related to Doppler spread. Coherence bandwidth related to delay spread. How do you find them? If I give you Doppler spread, you can find coherence time. If I give you delay spread, you can find coherence bandwidth. What's coherence bandwidth? The range of frequency over which your channel looks correlated. What's coherence time? The range of time instances or duration over which your channel looks similar, looks correlated. Maximum time over which this mathematically, I just said it by words, but this is by math. The autocorrelation over time greater than 0. This is the coherence time. When it's exactly equal to 0, signals separated in time by delta t, which means they are uncorrelated after passing through the channel. So we look at Doppler with respect to AC when delta f is equal to 0 and delta t anything, because it captures Doppler associated with a narrowband signal, autocorrelation over a narrow range of frequencies, and fully captures time variations, multipath, angles of arrival. So due to all these reasons, the most critical two information you need to get out of these two slides: what's coherence time, what's coherence bandwidth, how is it related to Doppler spread, delay spread, when Doppler spread happens, when delay spread happens. And of course, these are the math equations are to support the physics here. And I just said it by word now, explained it to you, but this is basically with just two variables. Everyone in the field can understand what this equation means. So basically, you need to understand both the explanations, the physics, and also the equations. And once you understand both, you start reading the equation and understanding, because they have meaning now. But if you don't understand them, they become isolated, just equations. We are not mathematicians now. We want to understand the physics behind the math. Clear? Now, having discussed delay spread, Doppler spread, it's time now to talk about the types of small-scale fading, to classify them further. Now you can classify them based on multipath time delay spread. Your channel, you can call it, you will read this in the papers or in the textbook, or some people when they are presenting their papers in the conferences, they might say, we considered flat fading channel. We considered frequency selective fading channel. You need to understand, what does this mean? What do the authors mean by saying flat fading? Or with respect to what I took in wireless, with what I studied in wireless, delay spread, Doppler spread, the teacher explained these things, but how are they related? These are just names for certain cases. For example, the first case, when the bandwidth of the signal, of your signal, the transmit signal, is less than the coherence bandwidth of your channel, we call it flat fading. Why? Because we don't have delay spread. Yes, because the bandwidth of your signal, this is the bandwidth of your signal, within the bandwidth of your channel. Do we have any distortion? We don't. because your signal bandwidth within the bandwidth of the channel. That's why we call it a flat in frequency. Your signal doesn't get affected. Or in other words, this happens when your delay spread is less than the simple period of your transmit signal, or simple period greater than delay spread. This means that you don't have delay spread. That's why you don't have distortion in the frequency domain of your signal, and because of that we call it a flat. Flat means doesn't get hurt, doesn't have any fluctuation in the frequency domain. Clear? Now we have also frequency selective fading. It's exactly the opposite of the previous case. When your signal bandwidth is greater than the coherence bandwidth of your channel, you get frequency selective. Why? Because in this case you have, this is your signal and this is your channel. When you multiply them with each other, because we are in the frequency domain, convolution becomes multiplication. When you multiply, this signal has to take the shape of the channel. So your signal becomes not flat like this, becomes selective. Selective in frequency over these are frequencies. That's why we call it frequency selective. Selective in the frequency domain. And in this case, we have delay spread. Delay spread is larger than the simple period. Or in other words, the bandwidth of your signal larger than the coherence bandwidth of the channel. Now this is with respect to delay spread. Now with respect to Doppler spread, people, researchers all over the world, they classify them into two types: fast fading and slow fading. So in fast fading, you have Doppler spread. Your simple period is greater than the coherence time. Your channel is like this, your coherence time. Your simple period is greater than the coherence time. So it gets affected. It's not embedded within the coherence time, it's larger than the coherence time. That's why you have fast fading. Fast fading, as the name implies, you have fast fluctuations in the amplitude of the signal over time. And this, as we agreed before, produces Doppler in the frequency domain. Slow fading, you have slow, as the name implies, you have low Doppler spread, and in this case the coherence time is greater than the simple period. And consequently, we say that the channel variations are slower than baseband signal variation. Yes? So now then, we have 4 new names for our small scale fading channels. We have flat fading, frequency selective fading, fast fading, slow fading, and each one of them has a condition to happen. And we relate them to coherence time, coherence bandwidth, simple period, and bandwidth of your signal. These 2 slides are very critical. Summarize things in words only, without math. As you can see here, didn't put math for the ones who hate math. Yes, question.
Slow fading is best than fast fading.
Less?
Best.
Yeah, slow fading. We like slow fading much better than fast because not much fading in the signal over time. Fading is a bad phenomenon. We said there is a huge like continuous variation in the amplitude of your signal, and this degrades your received signal quality. We don't like it usually, but I don't know, there are scenarios where you fast fading much better because it creates randomness in your system. If you were to generate randomness, random keys, this case is much better. It's much better if you are seeking for diversity. If you want to have diversity, you receive your signal over multiple paths in frequency, fast fading might seem much better if you are able to handle it. But if you cannot handle it, slow fading is better. Now, delay spread and Doppler spread, although they cause intersymbol interference, and inter-frequency interference or inter-carrier interference. They are bad, yes, but they are, on the other hand, they produce diversity in your system. What diversity means? You can receive your signal not only from the first tab that reaches your receiver, you can decode your data from the second one, third one, or you can combine all of them together coherently and amplify your signal and increase its quality, which is good. But if you can do it, you cannot always do it based on the techniques that you are using. So now this is by words. Our strategy, we start by math. You get scared, then we move to words to make it simple, but still you are not satisfied. Then we move to graphical representation to make no excuse for you. Now let's take a practical example where you have these figures. You have the channel amplitude versus frequency. And this is the first response of your signal. This is frequency response, by the way. You see the channel in frequency domain. Look at the green signal here, a green channel impulse frequency response. Which one has more variation over a frequency? The green or the blue? The dashed blue line. Dashed blue line has more variations. What does this mean? Since the x-axis is frequency, it's more selective in frequency. So which one is closer? All of them are frequency selective because, as you can see, there is variation over frequency. But which one has the large maximum selectivity in frequency domain? The blue. Too much selective. The variation in it faster than the variations in the red or green.
What do you mean by
Selectivity depends on the carrier frequency and changes over it quickly. This selective, I mean, frequency selective based on the frequency changes rapidly, not flat, means frequency dependent. For example, the red one, it seems like as if it doesn't depend on frequency. See the variation in it, the red one, not much. While the blue, see the blue is there. See the variations, unbelievable variation. So which one has more delay spread? Of course, the one has more variations frequency. To check that, take the autocorrelation function of these, channel. When you take the autocorrelation function of the blue, when you take the autocorrelation function of the blue, what do you get? This autocorrelation function. So the autocorrelation function at lower frequency values becomes independent, becomes uncorrelated. Yes, what does autocorrelation function means at the crossing? At the crossing means it's now uncorrelated. As long as it's below zero, it's correlated. After zero, it's not independent. So since this has too much variation, automatically the autocorrelation function will have lower coherence bandwidth. This is the coherence bandwidth, by the way, because until this point, you have similarities. After this, you have independent response. While for green, since green here varies little, the coherence bandwidth enlarges more, gets wider. While for red, since it's not varying much, has the largest coherence bandwidth. This is autocorrelation, this is frequency response, and this is delay spread. When you have the red, since you don't have too much variations, the red, what do you get here? Only 2 taps. While when you have green, you have 4 tabs. And 4 tabs, and see the delay spread a little bit larger. When you have blue, too much variation in the frequency domain, and you get here short coherence bandwidth, the delay spread is maximum. So what's the conclusion here? The larger the delay spread, the more selectivity your channel will be in frequency domain, and the smaller the coherence bandwidth will be. And the opposite is exactly true. Low variation in the frequency domain means close to flat, not selective in the frequency, has large coherence bandwidth, and consequently low delay spread, short delay spread, and of course smaller number of tabs. This explains by visualization. So you have 3 means to understand it. Either you understand it by visualization, or understand it by words, or understand it by equations, but by no means memorization. Yes, because you will get confused if you just memorize without understanding it, how it's happening. If I give you this, and give you the coherence bandwidth and tell you find the delay spread, can you find it? You can, because the coherence bandwidth is 1 over delay spread. Any one of them, you get the other, with factor, of course. Now this is with respect to delay spread. What about Doppler spread? In Doppler spread, you have, instead of variation in time, in frequency here, you have your channel in time, variation in time. And when you take their autocorrelation function, suppose you have a mobile moving with a speed 10 km per hour, and another mobile moving with 50 km per hour. The one who's moving faster, his channel changes more rapidly, and that's why its coherence time is shorter. Is that true? Does this make sense to you? More speed, very fast. The channel changes quickly. This means that since the channel changes quickly, the duration over which the channel is almost constant is short. And that's why the autocorrelation function here becomes independent after low period of time. Now, how does this translate to Doppler spread? The more variation in time, less coherence bandwidth, more Doppler spread. So this blue curve corresponds to this spreading. And this red one corresponds to this. This is with respect to Doppler. Does this make sense to you? If I give you this and tell you this is the coherence time, find the Doppler spectrum, Doppler frequency, you must be able to find that. If I give you the multiple curves and tell you match them to each other, you must be able to know. If I don't give you these speeds and give you only curves and tell you which one of these channels correspond to a mobile user moving with the high speed, you can figure that out. So just link the visualization with the word explanation, with the mathematical equation, you become expert in channel characterization. So the bottom line is that delay spread, Doppler spread are very important critical phenomena that happens due to wireless propagation. And we need to deal with both of them. And both of them sometimes appear not only due to the channel, but also due to sending your data with high speed. So there are factors influencing small scale fading. Small scale fading once you hear small scale fading, this means I'm talking about either envelope fading, Rayleigh, Raytian, Nakagami, these types, or delay spread, Doppler spread. If I have resolvable paths in time or frequency, I have delay spread, Doppler spread. If I don't, if all the multipath are reaching the receiver simultaneously at the same time, then you have only the fading phenomenon, because the signals can be added constructively or destructively, and accordingly you will have random distribution for your received signal amplitude. The random phase and amplitudes of different multipath components cause fluctuations in signal strength, inducing small-scale fading, signal distortion, or both. Is that this signal distortion due to delay spread, Doppler spread, fading due to, just I mentioned it, multiple signal, you receive them simultaneously at the same time. This is one factor that affects small-scale fading or influence it. The second factor, the mobility, the speed of your mobile. Relative motion of mobile with respect to the transmitter causes different Doppler frequency shifts, as just we explained in the previous slide by the curves, on each multipath components. Now, positive or negative shifts depend on towards or away from the transmitter. If you are moving away from the transmitter or moving to the transmitter. So when you are moving to the transmitter, you are squeezing. Your Doppler becomes less. When you are moving away, it becomes more. So not only this, but also the speed of the environment around you. You can be mobile, but also the environment can be mobile. How? If you have wind, if you have hurricane, if you have natural disasters, I don't know what, but this also caused the channel to change dramatically. The objective in the radio channel are generally in motion and can cause different Doppler shifts. If the speed of the motion is much less than the speed of the mobile, this effect may be neglected. If the speed of your environment, but in fact, if you are static and there is wind with certain speed, then you have to consider this in your design. Plus, the transmission bandwidth of the signal significantly influence the amount of your small-scale fading, and this is actually the limiting factor. If the transmitted radio signal bandwidth is greater than the coherence bandwidth of multiple paths, your received signal will be distorted. And this is the limiting thing of medium. This is why optics, cables, fiber optics are more expensive than copper. Why? Because the coherence bandwidth of optics is larger than the coherence bandwidth of copper, which means you can transmit your data with higher speed over optics while not having any intersymbol interference. While in copper, since the coherence bandwidth of your medium is short, you cannot send your signals with high speed, because high speed means you shrink the duration of your symbol. When you shrink the duration of your symbol, the bandwidth becomes large, becomes more than the coherence bandwidth of your channel. Your system gets messed up. You need equalization, special techniques to do. Since in the old days we didn't know much about equalization, and we don't like a complex equalization, it was really difficult to handle it. But we have techniques now that can handle this easily, but of course at certain prices you must pay as well. Is that understood? For example, the fiber, the logic fiber optics, we were talking about wireless, but this exactly applies to wireline communication, and why we need to use sometimes optics if you want to increase your speed, your transmission speed. This is how we relate things to each other, the same concepts. So To conclude, this is going to be maybe the last lecture about channel characteristics. After that, we'll move on into another subject. Wideband channels have resolvable multipath. Yes, and statistically characterize the time-varying the time-varying impulse response of the channel for WSS-US, wide sense stationary, and in wide sense stationary means zero mean and autocorrelation not dependent on time, dependent only on the difference. And this spread happens due to having multiple clusters. Multiple clusters, what happens to multiple clusters? In this case, you will have resolvable multiple paths at your side, and you get the small scale, the full small scale behavior of your channel. Scattering function characterizes RMS delay and Doppler spread, key parameters for system design. Delay spread, Doppler spread, and the fading. Delay spread defines maximum delay of significant multipath components. The inverse of it is coherence bandwidth. Signal distortion in time and frequency when delay spread exceeds inverse signal bandwidth. Doppler spread defines maximum non-zero Doppler. Its inverse is coherence time. Channel decorrelates over channel coherence time, as we have seen in the figures I just presented to you. Plus, radio channel varies, but how often and how much, this depends on the mobility of your environment or your transmitter and receiver. Knowledge of channel variation is extremely important so that you can design your system at the transmitter and receiver in such a way you mitigate these impairments of your channel. Many current systems assume the worst case channel scenario or variation. For example, they say we don't have special techniques where we can exactly at any point of time know what's the delay spread and Doppler spread. So to avoid this problem, just do exhaustive measurements for your channel, and from these measurements you find the maximum delay spread, maximum Doppler spread, and design your system according to this situation. Of course, this system, although it will be robust under any situation, but it's not efficient. Why? Because there are times where you don't have this much spread. Why do you need to squeeze and limit yourself with this design? A much smarter way to handle this situation is to use adaptive, flexible design, but this will come at the cost of overhead signaling and communication between the transmitter and receiver. So this also comes with the need for channel estimation, tracking at the receivers, channel prediction, like the one you are working on it, algorithm. Now, I don't know, but as far as I know, nobody, for example, has implemented the technique you have proposed for channel prediction. If we do it and compare with the other existing techniques and show much better performance, that will be a great contribution. We need adaptive interleaving based on channel variation, cell assignments, and the handoff in cellular and other techniques as well to be able to handle and overcome these impairments in the wireless channel. So with this, we finish the first part of the lecture, and thank you very much for your attention.